Hi, my name is Anastasia, and today I would like to cover some topics of electrochemistry basics of electrolysis. And to start with, let's look at the electrolyzers itself. Today I will be covering only low temperature electrolysis, but what you need to know that there are different types of electrolyzers as well, for example, solid oxide electrolysis, as well as high temperature electrolysis. But in this particular case, we will be looking at these two devices, which do exactly the same job of water splitting, but they get there via different means. For example, on our left side, you can see alkaline electrolysis example, a device that uses diaphragm and a lot of very concentrated alkaline solution, where on our right side, we can see a proton exchange membrane electrolyzer, which is a more compact device and uses a membrane that conducts protons. However, at the end, as I said, both of these devices, they perform exactly the same function of splitting water. Now, let's dive into the electrochemistry, and first, we're going to discuss thermodynamics of water splitting. There are two potentials that we need to know in the thermodynamics. First is a reversible potential, which is pretty much our equilibrium potential of 1.23 volts to split water, and the other one is a thermoneutral potential, which corresponds to the enthalpy of the reaction. Looking at this graph, what we have to understand is that as the temperature rises, the potential of water splitting is going down, which means that it's easier and easier to split the water at a higher temperature. However, at the same time, to actually convert and produce 1 mole of hydrogen under standard condition, it requires a total energy of 285 kilojoules roughly, in which there are a portion which comes from the electricity, so our delta G, and also at the same time there is some energy that is coming from the heat. So in this case, if we look at the black curve, that would be our thermoneutral potential, which, as you can see, is significantly higher than our 1.23 volts, which means that in reality, because we do have some losses associated with the heat of the reaction, if you drive the reaction above thermoneutral potential, generated waste heat from the overpotential, it's actually something that would help us to drive the reaction. And it has to do with the fact that the system is real and it does not behave as it would in the ideal case. Now let's discuss polarization curve. Polarization curve, it's something that represents a steady-state relationship between the potential and current density of the cell. Also, this curve is governed by the same three major electrochemical principles as thermodynamics, kinetics, and mass transport. As you can see on this graph, our ideal scenario, our perfect scenario, it's 1.3 volts, a straight line of water splitting. However, in reality, there are so many different losses associated with different components of the electrolyzers that polarization curve looks completely different. Let's discuss it. As you can see, our first losses or our first differences are coming from the activation over potential. Activation over potential is related to hydrogen evolution reaction and oxygen evolution reaction, and usually it has to do with the electron or charge transfer to the electrode itself. And this is portion that, of course, that is governed by the kinetics of the process. As you can see next, we have our ohmic over potentials. Ohmic over potentials, they're typically governed by the ion transport through the electrolyte of the device. The electrolyte of the device could be a diaphragm in alkaline water electrolysis, or it could be a membrane, for example, in a proton exchange membrane water electrolysis. And this is something that is governed by the transport of the reaction. Next is concentration over potentials. In other words, it could be called a diffusion over potential, and it has to do with the mass transfer of gases or the reactants, which is water in this case, in the device. So this polarization behavior of the electrolyzers helps researchers to understand where the losses are coming from and helps to identify future research directions. Thank you.